In today's lesson, I'm going to state and prove two extremely important theorems to linear algebra as well as calculus. The first is the Koshi-Schwarz inequality, and the second is the triangle inequality. You need to learn the statement and the proof of both theorems. Then we're going to use the concepts that we've just proven to define orthogonal vectors. Orthogonal vectors are vectors that meet at right angles to each other, and we discussed the conditions that vectors must meet to be orthogonal. We'll start with the Koshi-Schwarz inequality. If u and v are vectors in n space, then the absolute value of u dot v is less than or equal to the magnitude of u times the magnitude of v. Now let's make sure we're talking about the same units here. U dot v is going to be a scalar. The absolute value of a scalar is a scalar. The magnitude of u is a scalar. The magnitude of v is a scalar. So again, scalars. So we're just comparing scalars to scalars. Let's look at the proof. Now this is a rather ingenious proof. It's one that you would probably not think of on your own, but it's one that is easy to follow. Just think, if all of us could think of it on our own, then we would have our name on it rather than Koshi-Schwarz. Okay, if u is 0, then one gets 0 equals 0, and the theorem is true. So if u is 0, then 0 dot v is 0. The absolute value of 0 is 0, so we get 0 on the left. If u is 0, the magnitude of 0 is 0. 0 times anything is 0. We get 0 on the right, so we get 0 equals 0. We only had to prove that it's either less than or equal to. We have equals, and the theorem would be true. So what we're going to do then is assume that u is not 0. Well, if u is not 0, then we're going to consider the vector tu plus v. So tu plus v will be non-zero. U is not 0, so tu plus v will not be 0 unless, of course, t is 0. So we'll assume also that t is not 0. T is a non-zero real number. Now we know that tu plus v dot tu plus v is positive, because tu plus v dot tu plus v would be the magnitude of tu plus v quantity squared. So that's going to be positive. So now I can use the FOIL method. Actually, it's the distributive property of dot product, but we can remember it by FOIL. And I can say tu dot tu, well, t times t is t squared, so that would leave me with t squared u dot u, plus this would be tu dot v plus v dot tu. Well, that's going to be 2t u dot v, and then v dot v is positive, because I'm just multiplying these two to get this one. So if this quantity is positive, then so will be this quantity. Now that's pretty straightforward. A lot of us would have thought to do that. Now we'll let a equal to u times u and let b equal to 2uv. Now not many of us would think of making this substitution. Well, if a is u times u and b is 2uv, then we're going, and let c be v dot v, we'll get at squared. U dot u is a, so I've got a t squared. 2uv is b, So the 2uv is to b, so I've got bt, and v dot v is c, plus c is greater than or equal to 0. I'm just making that substitution. Well, notice now we have the quadratic equation. The quadratic has no real roots, or only one real root. Now notice the quadratic is always greater than or equal to 0. Now if it's strictly greater than 0, then the graph of it would be coming like that. Because if it's greater than 0, that means the quadratic is always positive. Now if it were equal to 0, then it could touch it. Well, in any case, it's going to either have no real roots or only one real root. So the quadratic either has no real roots or only one real root. Well then, if it has no real roots or only one real root, then the discriminant, b squared minus 4ac, is less than or equal to 0. Remember, if the discriminant is positive, then you have two real roots. If the discriminant is equal to 0, you have one real root. If the discriminant is less than 0, you have imaginary or complex roots. So either has no real roots or only one real root. So we have b squared is less than 4ac. Just added 4ac to both sides. And that would imply that now b squared, remember what we let b be. B was 2 u dot v. So b squared would be 4 u dot v quantity squared is less than or equal to 4. In place of a, we have u dot u. In place of c, we have v dot v. This should be v. Now this would imply that divide by the 4 and take the magnitude here. This would imply that u dot v quantity squared would be the magnitude of u dot v squared. U dot u is the magnitude of u squared. V dot v is the magnitude of v squared. That's the theorem I proved for you previously. So divide both sides by 4 and use the fact that u dot u is the magnitude of u squared and v dot v is the magnitude of v squared to get this relation. Okay, now just take the square root of both sides, which I can do because everything would be positive, and I get u dot v is less than or equal to the absolute value of u dot v is less than or equal to the magnitude of u times the magnitude of v, which is what we were trying to prove. Now let's back up to a fact that we used to find the angle between two vectors u and v. Okay, we had that cosine theta, theta is the angle between the vectors, was equal to u dot v divided by the magnitude of u times the magnitude of v. Let's multiply both sides to clear fractions. So multiply both sides by the magnitude of u times the magnitude of v. We get u dot v is the magnitude of u times the magnitude of v cosine theta. Or since multiplication is commutative, it didn't matter which order. So we can have u dot v is the magnitude of v times the magnitude of u cosine theta. Now that's just multiplying through by the denominator to clear fractions. Okay, now let's just consider this side. U and v meet at right angles if and only if theta is 90 degrees. So that's the definition of right angle. The two vectors will meet and form an angle of 90 degrees. A 90-degree angle is called a right angle. And we say that if u and v meet at right angles, that u and v are orthogonal. Well, if theta is 90 degrees, then cosine theta is 0. So theta is 90, implies that cosine theta is 0. 0 times anything is 0. So that would be if and only if u dot v is 0. So we have u dot v is equal to the magnitude of v times the magnitude of u times cosine theta. U and v would be orthogonal if and only if theta is 90 degrees, which implies that cosine 90 degrees is 0, which implies that u dot v is 0. Now the argument above only applies to non-zero vectors, because if you'll go back and look for the angle between vectors, the concept of an angle between vectors only makes sense when u and v are non-zero. But by definition, we will expand the concept to include the zero vector. And I'll define orthogonal for you. U and v are orthogonal if and only if u dot v is 0. So that's how we're going to define orthogonal, if and only if the dot product is 0. Let's determine whether the vector 3, 2, negative 1 and the vector 1, negative 1, 1 are orthogonal. Well, what we have to do is check the dot product. If the dot product is 0, then the vectors are orthogonal. So we'll do the dot product. 3, 2, negative 1, dot, 1, negative 1, 1, which would be 3 minus 2 minus 1, which is 3 minus 2 is 1, 1 minus 1 is 0. So we say the dot product is 0, therefore the vectors are orthogonal. Let's find all vectors orthogonal to 3, 2, negative 1. Well, we'll let A, B, C be the non-zero vector orthogonal 2, 3, 2, negative 1. Well, then we know that 3, 2, negative 1, dot, A, B, C is equal to 0. Or I have that 3A plus 2B minus C is equal to 0. Or I have that 3A plus 2B is equal to C. We'll let A equal to S and B is equal to T. So we can get the form of the vectors would be S, T, 3S plus 2T. So the set of orthogonal would be the set of all vectors S, T, 3S plus 2T, such that S and T are real numbers. Now let's prove the triangle inequality. Let U and V be vectors in n space. Then the magnitude of U plus V is less than or equal to the magnitude of U plus the magnitude of... Okay, now let's look at the proof. Let's consider the magnitude of U plus V squared. The magnitude of U plus V squared is going to be U plus V dot U plus V. Now that's using the property that we proved in the previous tape. Using properties of dot product, we can write this as U dot U plus 2 U dot V plus V dot V. U dot U, this will be U dot V plus U dot V, which would be 2 U dot V, and then V dot V, which is going to be the magnitude of U squared plus 2 times U dot V plus the magnitude of V squared. Which is going to be less than or equal to the magnitude of U squared plus 2 times the absolute value of U dot V plus the magnitude of V squared. Now let's see why this would be the case. If U dot V is positive, then we would have equals. If U dot V were negative, then we would have less than. Because if U dot V is negative, then that would be subtracted from the magnitude of U plus the magnitude of V, which would create a smaller number. So in either case, it's either less than or equal. Again, if U dot V is positive, then the absolute value of positive is positive, so we're going to have the equals case. If U dot V is negative, then this negative is going to take away from the magnitude here, which would give the less than case. By the Koshi-Schwarz inequality, this is going to be less than or equal to the magnitude of u squared plus 2 times the magnitude of u times the magnitude of v plus the magnitude of v quantity squared. Because the Koshi-Schwarz inequality said that the absolute value of u dot v was less than or equal to the magnitude of u times the magnitude of v. And of course, this can now be factored, so it would be equals the magnitude of u plus the magnitude of v quantity squared, just by factoring. How do I get the magnitude of u quantity squared? Magnitude of u times the magnitude of u and so forth. So that's just a guessing check factoring. Let's look at what we have then. Putting all this together, I have the magnitude of u plus v quantity squared. Since I have some less thans in here, would be less than or equal to the magnitude of u plus the magnitude of v quantity squared. Now these two quantities are obviously positive, so taking the square root of both sides, I get the magnitude of u plus v is less than or equal to the magnitude of u plus the magnitude of v, which is what we're trying to prove. We have another theorem that's free now. U and v are orthogonal if and only if the magnitude of u plus v quantity squared is equal to the magnitude of u squared plus the magnitude of v squared. So this gives us another test for orthogonality. If the magnitude of u plus v squared is equal to the magnitude of u squared plus the magnitude of v squared, then u and v are orthogonal. This is sometimes called the Pythagorean check. Notice the similarities with the Pythagorean theorem. Well, this result follows directly from the last proof. And all we have to do is to go up and look at one step in the proof. U plus v, magnitude u plus v quantity squared. It's down here. Well, the only way this is going to be equals will be for the middle term to be 0, which means u dot v is 0, and the only way the middle term can be 0 is for the vectors to be orthogonal.